Okay, so welcome to Emergent States of Matter. This is lecture something or other, and February the 10th, 2021. So last time we were starting to talk about the systems with continuous symmetries. And so what we talked about was the Heisenberg model of a magnet being a model where you have discrete spins being now replaced by vectors that have, in the Heisenberg case, typically, say, 3 dimensions, which we call S, X, S, Y, S, Z. And the Hamiltonian for that is then just that the spins interact through their dot product. So Si dot Sj as shown over here. And then they also interact with an external magnetic field H. So this is just a generalization of what we saw with the Ising model. And then the point that I wanted to make about this that's critically important is that because the interaction energy depends only on the angle between spins, what that means is that when I make a global rotation of all the spins by the same angle, then that will not change the interaction energy. It won't change the Hamiltonian. In other words, what that means is if I take the spins as shown over here and then make a global rotation as shown over here, that doesn't change the Hamiltonian. So in other words, the Hamiltonian is invariant under the rotation group acting on the order parameters. And so this is the concept then of when we talk about spontaneous symmetry breaking, you first have to ask, well, what is the symmetry that we're breaking? And the answer is it's a symmetry of the Hamiltonian. And that symmetry of the Hamiltonian is just another way of saying that what changes can I make on the degrees of freedom so that the Hamiltonian doesn't change. So this example here that I've shown you is a rotation, but I wanted to emphasize that it's a rotation in spin space and not in lattice space. So what you can see in these pictures over here is that at the top here is that the lattice stays the same, but it is the spins that rotate. So basically what we're talking about is a symmetry of the order parameter. In other words, if I rotate an order parameter space, that does not change the energy of the system. You can also think of other symmetries that are space-time symmetries. For example, translational invariance. Take the system, move it over here, does it change the energy? So the answer is no, it doesn't. The system is translationally invariant. That means that the system, you can shift it around, it won't make any difference to the energy. So that's an example of a space-time symmetry. So we can just say that that space-time symmetries are like, for example, translational symmetry, rotational invariance, and these are distinct from order parameter symmetries. So that point is critically important. In the example of the Heisenberg model, we were sort of thinking that the thing is a magnet sitting in 3-dimensional space. So you tend to think of the magnetization vector as also living in 3-dimensional space, but it doesn't actually have to. So what this implies is that the dimension of order parameter space and real space, if you want, can be different. And so let me give you an example, and that is the XY model. So we call it the XY model like that. And where that comes from is I may have a lattice, and I may have certain interactions between the spin orbit coupling in such a way that the magnetic moments are only rotating in a plane, even though the spins themselves live on the vertices of a three-dimensional lattice. So in this particular case, interactions and their anisotropy mean that the spins are restricted to living in a plane. So we call that the XY model. So in other words, the vector S is now a vector with two components, S1 and S2. The absolute value of S is still in appropriate units just 1. Each of these components, this lives in d-dimensional space, where d could be 1, 2, 3, or higher if you wanted to, for whatever physical reason, you might want to do that. And so what you would have then is the Hamiltonian looks like this. Same thing we saw before. I didn't really need to write it down, did I? So I goes from 1 to n is the labels of lattice spacings, of lattice points, lattice vertices in d dimensions. And S is just this vector like so. So here you have, hang on 1 second. So,
yeah.
so that n was equal to 2. This is the dimension of order parameter space. And d might be 3. That might be the dimension of real space. And in the homework, one of the first questions in there is to look at what happens when you have an object of n dimensions embedded in a space of dimension d, which can be different. And so the critical outcome of this, n does not have to be d. So that's the first thing. And the second thing is that this can give rise to topological defects. So I'm going to say a little bit about that, but somebody had a question, so let me answer the question first.
Yeah, I had a question. So going back to like one of the first things you wrote, the space-time symmetries being distinct from the order parameter symmetries, and the implication is that this means that the dimension of the order parameter space is not the same as the real space. Why is that? Why does the symmetries being distinct tell you about the dimension of the state and not just the topology of the state, right? Because we could have, can you have like a three-dimensional space that just has some strange topology and therefore the symmetries are different, but they have the same dimension in principle?
Yeah, it doesn't. I mean, I don't know. I don't know about other spatial topologies, but well, yes, I do actually. We will talk about that. Yes, the implication for the most important thing I'm trying to imply to you is that those spaces are different, and when you study the topological outcome, that can that depends on that interplay between the topology. And one of the ways it depends on that is through the dimensionality, but it can also depend on the topology.
Right.
For example, we'll see an example. We'll talk about superconductors in an annular geometry.
Right.
So you've got a geometry which has a topology which is not simply connected. And the outcome of that means that you can have persistent currents, but those persistent currents can actually decay through the dynamics of topological defects in that thing. So there is an interplay between both the topology of the space and the topology of the order parameter space. So it can get quite complicated. Yes. So does that answer your question?
Yeah. Yeah. Cool.
Okay. So then let me talk about what I mean by topological defects. So the homework is about topological defects, and it's not that complicated. What you're being asked to do is essentially, plot out the order parameter configurations and notice something interesting about them. So I just want to take a few minutes to say what we mean by defect and what do we mean by topological defect. So the question is, what is a defect? And so the answer is, let's suppose we have an order parameter. And let's suppose I call it psi of r. So it's some variable psi that varies in space like that. Okay, so you might say, well, okay, fine. So here's space, here's psi, and it's just some constant like that. And the fact that this is 0 here and this is some psi naught, the fact that this is non-zero means that I have some long-range order in the system. Okay, so that's if psi of r is equal to a constant. So what I've drawn here is basically here psi of r is just equal to psi naught everywhere. So now let's ask what happens if I were to make psi varying in space. So what I might get is a graph that looks like this. So here is psi of r is not a constant. It's literally spatially varying, but in this region here, you can see that it actually goes to 0 at this point. So what that means is, because psi of r is equal to 0, that means that at this point over here, where I have an absence of order. And so that means it's a hole in the order, if you like. And so we call it a defect. So an example of that might be crystalline order. And you might say, oh, I'm going to monitor crystalline order by the Fourier transform of the density. So you may have, atoms organized in some array like so, and then you may have a defect. Might be that there is a missing atom, say over here. So that would be an example of a vacancy, or in other words, an example of a defect, but not a topological defect. So that's what we mean by defect. So now you could say, what is a topological defect? And the answer is it is a defect in the order which you can detect by a non-local measurement, if you will, and that measurement is usually done as some sort of line integral. So let me give you an example. So let's just say it is a defect that has a global impact on a measurement that is made non-locally. Okay, that's not a very good definition, but that really says the essence of it. So let me give you an example, and some of you may know these examples, others may not. So an example might be a dislocation in a crystal. So I'm going to probably get this wrong if I try to draw this, but let's do it anyway. And those of you who know what I'm trying to do, please feel free to interrupt if I get the drawing wrong. Okay, so here is a drawing, and so now you can see that this is a slightly different picture. This is not just a vacancy; it's actually a line of missing atoms. And so if I were to draw these lines, it really wouldn't look like this, because what would happen is that the gap here would not, the atoms would sort of squeeze in to fill in this gap. So if I were to draw what it looks like, actually what this would look like is something like this. So what would happen is in going from the top picture to this bottom picture, what's sort of happening is the atoms readjust their position. Okay, so nothing fancy about this. But what it means is if I count along here, I see there's 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6. So there's 6 here, and there's 7 here, and so there's a line of missing atoms. So this is an example of a dislocation. And now I want you to imagine that this is going out of the paper. So this is just a 2D slice of the same configuration in 3D. Okay, so this thing is just going up like this. So what's topological about it? So so the answer is that you ask, well, what happens as I make a circuit around the dislocation? And what we're going to measure is a thing called the Burgers vector. Okay, now this is the part where I will almost certainly get it wrong, because I'll just draw it wrong and get confused. So let me try to draw that for you. So let's suppose I'm going to expand this picture. Okay, so let's suppose I were to take a system without a defect, and I were to start over here, and I go one step this way, one step this way, one step this way, and one step this way. So I make a circuit I make it actually it'd be better if I did it with two. Let me do it with two. Okay, so I start here. I make a circuit of 2 steps down, right, up, left, and of course the end result is I get back to where I started. So this is the case where there is no defect. Okay, so now I'm going to do it with a defect, and this is where I'm going to mess it up, because I remember when I did this last time, because I'm teaching and so I'm nervous and so on. So I get flustered and mess it up. So all right, so that's now this picture here. I'm just putting one more up here. Okay, so the dislocation is basically at this point where this is where the dislocation is. So let's try to do this. So let's go down 2, go right 2, go up 2, and then go left 2. Okay, so it worked. Okay, so now what happened is you can see that what happened in here did the same circuit around the dislocation, and did not get back to the start. So the Berger's vector, the thing that tells you that is the fact that I meant to go. I didn't end up here. So the Berger's vector is this vector over here, which is the expert displacement added to my configurations because of the existence of the topological defect. So notice that we went round the topological defect. So basically the bottom line is, if the circuit includes the topological defect, you get a non-zero value. B, the Berger's vector. If the circuit does not, then you just get, well, saying B is equal to 0 is probably misleading. You get no displacement. So why is it topological? It's topological for the interesting reason that here we have our circuit was 2 steps in the different directions. So you might say, well, okay, what happens if you make the circuit 100 steps in the different directions? So if you do that, what you find is that B is still equal to 1. unit vector in the x direction. So in other words, the Burgers vector is invariant under the circuit. So basically, if you think about our simple picture, so here's our material, like so. I tell you that there's a topological defect around here, so there's the defect. And then if I make any circuit like this and measure the Burgers vector, all these circuits have the same B. It just depends on the nature of the dislocation and is therefore topological. Topology means deforming contours. So what that means is I can deform these circuits, C1, C2. I can deform C1 into C2, and the topological charge doesn't change. The topological Burgers vector is invariant, and things that are like that, we call them topological charge. So what does that mean? Topological charge is equal to 1. Well, there's nothing to stop me making a Burgers vector where the gap is equal to 2. You could make a very deformed dislocation where the gap is 2 and not 1. And that would also be topological. Okay, so that's the basic idea then of a topological defect, at least shown in this very trivial example of a dislocation. Any questions about that before I move on? Okay, so then if there's no questions, then let me go on. Any questions? No. Okay.
Can I ask a question?
Yes, go ahead.
So if the gap is 2, the topological charge is still 1, or it will be 2?
It will be 2.
Okay.
The topological charge in this case is how far away from the starting point you end up when you make the circuit.
Okay, thank you.
Okay, and what I drew for you was an edge dislocation. You can do the same thing with a screw dislocation. So the edge dislocation was I just made a line of missing atoms. I can make a screw dislocation where I take every plane, and then at some point I cut them and make plane n line up with plane n plus 1, and plane n minus 1 line up with plane n. And that gives me a screw dislocation. And that screw dislocation is like a multi-story car park where you sort of keep driving around, you get a helix. That would be called a screw dislocation. So this example here is an edge dislocation. It can also be screw dislocations, which is sort of like a helical multi-story car park. And these are just dislocations in space. Now you can also have dislocations in order parameter space. So as an example, which is what you're going to be asked to think about in the homework, let's suppose I have a complex field as an order parameter. So I have a field psi, which can be an imaginary, a real part plus an imaginary part, so psi1 plus I psi2. And then I can say, well, that's a function of space. So it's now a function of space. And so what that means is that the defect in this, so that's a point where psi of r is equal to 0. And so then you might ask the following question. Suppose I'm in d equals 2 or d equals 3. What kind of manifold is this defect? And is it topological? So let's talk about the first question. What do I mean by what kind of manifold? Well, what I really mean is this. If you tell me that psi of r is equal to 0 at some point in space, then that means if I'm in, say, two-dimensional space, so here is my system. There's x and y, and now you're telling me that here's a topological defect sitting here. So at that point in space, psi of x and y, let's call this point x1, y1. So psi of x1 and y1 is equal to 0. And what that means is that, i.e., both components the real and imaginary part are zeros at x1, y1. So that's what we mean by saying there's a defect there. Now, you might ask yourself, well, what does it look like in 3 dimensions? I'm not going to tell you the answer, but I'm going to ask you to think about just writing down the equations I'm showing you here, just saying what the defect means. Now ask yourselves what happens when I have 3 coordinates, x, y, and z, rather than just x, y. And then what you'll see is, you'll see what kind of object this is. Here, this object is a point defect. And what you might guess is, well, what would you guess would happen in 3 dimensions? Anybody?
Line.
Right. So you might guess the defect is a line in 3D. So you can confirm it. And that's the homework. So then what you're asked to do is then think about different configurations of an order parameter. So an order parameter, which is a complex number, has a modulus and a phase. So now let's ask what the defect looks like in these representations. So let's go back to our picture. So here is our system like this, and I'm just going to draw this in d equals 2 because it's too complicated to draw for now in a higher dimension. So what do we expect the order parameter to look like? So locally, what psi of r is in the Argand diagram, so this is the real part of psi, the imaginary part psi. So basically, it looks like a vector that points like this, and its magnitude is that direction. Its magnitude is the length of that vector, and the angle, the argument is the angle theta. So let's say that psi of r, let's just say its magnitude is psi naught. So what that means is that if I look at this picture here, I can take any point in space, and I can draw which way the order parameter points. So maybe here it points like this, and maybe here it points like this, maybe here it points like this, and so on and so forth. Okay, so I can literally draw this vector picture of this complex order parameter in space like this. So now the question that you need to think about is, well, what happens? Is that doesn't look like it's, you can see that when you make it brighter. So what happens as a defect? Well, at the defect, psi of r is equal to 0 for both the real and imaginary parts. And so what that means is that the phase is not well defined. So this thing here, this theta, that's what we're calling the phase. And so for all of these vectors here, we can draw the phase, and we can draw its magnitude, its modulus. But if there's a topological defect, then we can't do it. So at a topological defect, you kind of have like some kind of coordinate singularity in the representation of the order parameter. So actually, just to fill in this picture, what you would see is, let's suppose there's a topological defect right here. Then you may see, for example, these things looking like something like this. And then in the middle here, you don't really know what to draw because you can't define it. And so this thing over here is then the topological defect. And so that's what we mean by topological. Now, what is the quantity that you measure in something like this? Well, so the answer is you can basically measure the winding of the phase as you go around this object. So so if you integrate the angle theta as you go around this a curve circling the topological defect, so here's the topological defect. Let's put in a curve that goes around it like so, and then let's draw over here another situation. And there's the topological defect, but now this time I draw a curve that goes round like so and does not include the topological defect. Let me draw my curve again. So there we go. So this one includes the topological defect. And this one does not include it. So what do you think is going to happen to the integral of theta? As I go around this curve here, so my angle, so I'm going round and round like this, and then retracing my steps. So in this case, I'll get nothing here. So my winding number is 0. But over here, in this picture, if you look over here, in this picture, you can see that as I go around this defect, the angle is always increasing. So in this angle, so in this one, the answer is it goes round by 2 pi. In this picture over here, I want you to satisfy yourself about this. If I don't enclose a topological defect, the angle will go up and then it will go down, and so it'll end up that I won't end up winding around it. And so this winding number as you go around the circuit is a topological feature that doesn't depend on how large the contour is. And if the circuit is deformed in some way, but as long as it just goes around it, then it will always give you the same result. So you've seen something like this before in electromagnetism. You've seen, for example, Gauss's law, okay, where the Gauss's law, you do the Gauss's law thing, and you end up calculating the total charge enclosed by a surface. So this is sort of like Gauss's law. So it's a similar kind of thing. Okay, so that's what I want to say then about topological defects, which is something that will help you in doing the homework, and then in the homework you're asked to draw these things and also look at what happens when I have multiple topological defects by drawing out the configurations. So any questions on that before I go on to the next thing I want to talk about?
So if I have an order parameter like a two-dimensional vector with a fixed length, then does the definition that the topological defect is that at that point the order parameter vanish still applies? Because in this case, the order parameter is always non-zero.
You're correct. So what I said here was locally this is true, but for this picture here, in reality, so what's in this picture where you have spins, it's like there's a missing atom, so there isn't a spin there. So in a real system, like a superfluid, both the amplitude, the modulus I called it, the modulus and phase can vary in space. And so and so at the defect, the modulus is equal to 0 and the phase is undefined. And in a real superfluid, the vortex core has a particular dimension. It can be it can be like an angstrom. It can be hundreds of angstroms if you're talking about a superconductor. So it can vary. So what I would say is that in real life, the size of the core of the topological defect is not universal and depends on the system. So it might be, for example, say an angstrom or so in superfluid helium-4, and it might be, say, 1,000 angstroms in a superconductor, or superfluid helium-3 or something like that. Actually, I don't remember what it is in superfluid helium-3, maybe not quite as big as that. But anyway, okay, any other questions about this before I move on?
Are topological defects always of dimension 1 less than the space they're embedded in?
No, they don't have to be. Okay, so that's one of the things to think about.
Then is it no longer a line integral?
There's different ways that you can detect them depending on their dimensionality. So we'll talk a bit about that later on, but that's not what I want to talk about right now. Okay, so the next thing I want to talk about is another example of a continuous symmetry. And the example that I want to talk about is superfluid helium-3. So let's now talk about what a superconductor is, or what a fermionic superfluid is. So what we're going to talk about now is the basic idea of superfluids and superconductors. I'm going to tell you this in very low-level way, but don't be misled by thinking that it's trivial. It's not trivial. So in the first question in the homework asks you to think about the things I'm going to tell you about, and try to deduce a line of argument that I came up with back in the late 1980s, 1987, to estimate what is the pairing state of the high temperature superconductors, which in fact started this whole field of unconventional superconductors. So let me just tell you some of the basic ideas about superfluids and superconductors, which we will see in more detail later on. So the basic idea of superfluids and superconductors is that they form as a result of Bose-Einstein condensation. Which you all know because you've done it before in your introductory graduate stat mech class. So they form as a result of Bose-Einstein condensation, but an extended concept of that to include interactions. So you'll remember that Bose-Einstein condensation is what happens to isolated ideal bosons, and we're going to be talking about in superfluids and superconductors about interacting bosons. So we have to extend this concept. But the basic idea is that you form some sort of Bose-Einstein condensate. So anybody in the class not know about Bose-Einstein condensation? Okay, well, if you don't know, you don't have to out yourself right now. But if there's anybody who's not happy about it and doesn't understand it, please let me know. Make a comment in the team chat. I can give you the lecture notes from my old class. You know, make sure you know this, because what we did in the elementary 504 stat mech or whatever graduate stat mech class you took, and I don't have time to really go over that again. I'm going to assume that you know that. So that's the first point. The second point is that if we have bosons, if we have bosonic atoms, e.g. helium-4, then they just Bose condense. But including the interactions. Okay, helium-4 is strongly interacting, so it's not really Bose-Einstein condensation. They just Bose condense. I'm going to put that in quotation marks, and what we'll see is that what they actually do is form a state with something called off-diagonal long-range order, which I'll abbreviate as ODLRO. And next lecture we will describe that precisely using annihilation and creation operators and define how you measure it. Okay, so that's what happens for something like helium-4. Now, suppose you don't have helium-4. Suppose you have a fermionic system. Such as electrons in a superconductor, or helium-3 atoms. Okay, so then what? So what can happen is, through a process that is not easy to explain, the fermions can, through interactions, form composite bosons. So, example, in a superconductor, the electrons interact through sound waves, and in superfluid helium-3, you have spins, nuclear spins, interact and stabilize pairs of helium-3 atoms. Okay? So those are very complicated. You have to know a lot about the material in order to understand that. But the basic point is that you form composite bosons, and those composite bosons have a name. These composite bosons are called Cooper pairs. And Leon Cooper was a postdoc here at Illinois, working with John Bardeen and Bob Schrieffer, and he came up with the idea that that if you, again, we'll talk about this in class, if you have two electrons above a Fermi surface, they can actually form a kind of bound state in momentum space, and that is called a Cooper pair. So this is basically a sort of it's hard to say in its general terms. Let's say it's a bound state. Really, I think of it really as being of time reversed states, about bound state of electrons. In time reversed states, typically. When we talk about superconductors, I'll give you a physical feel for this. And so what you can think of then is if I have my box, and then what I have is electrons floating around in that box. And so here's an electron over here with a spin up. Here's an electron over here with a spin down, and then it forms some blobby object, which is the composite boson. Let's call it the Cooper pair. And this thing is a composite boson. And then I've got a bunch of these things floating around. Of course, they don't really look like this, but let's draw them like this as if they did. And then these objects can Bose-Einstein condense. To make a superconductor, or a superfluid in the case of these objects being helium-3 atoms. So that's the idea. And let me give you some historical fact. So in classic superconductors, the separation. Let me draw the separation can be something like 1,000 angstroms. And so these Cooper pairs strongly overlap. In the high temperature superconductors, in high temperature superconductors, this distance L is about 10 angstroms, actually even slightly less, and it's very anisotropic. It doesn't really matter, but it's very small, and so the Cooper pairs are very localized. So the picture that you might have, if I were to draw two boxes of these things, it would look like this. I'm going to just draw the outlines of the Cooper pairs. So something like this would be in the high TC superconductors, very localized. In the classic superconductors, they're sort of strongly overlapping like that. So that's the difference. So one thing, of course, that means is that when they are like this, there's the electrons inside the Cooper pair. These electrons are interacting by Coulomb interactions. So in the homework, you're asked to think about what happens when the electrons want to form these pairs. And so the question asks you to think about that, and I'm not going to say any more about it. But one of the things that I want to just tell you about it before we leave the subject is that, of course, I've drawn here the electrons are in a singlet state. And you might ask why. You can have electrons in a triplet state. And if they're in a triplet state, then what would they look like? Well, because of the pairing, because of the way the angular momentum adds up, they would look something like this. So anyway, that's all I want to say about the superconductors. Now I want to talk about what happens in helium-3.
May I interrupt?
If it's quick.
Yeah, it's pretty quick. So I want to know how people can measure the separation length about 1000 micron and 10 micron. How do they determine that?
It's very complicated. Okay, I can't. There isn't a very quick answer to how you measure it. You can do it through in a superconductor. You can do it through microwave measurements and frequency dependent measurements of electromagnetic response. There's a lot. It's quite involved to say how we know this to be true. Okay, so the determination of the length scales in superconductors and superfluids, it's not obvious. It's not trivial to say there's a simple way to measure it. Okay, so can't really answer for now. Okay, so now I want to tell you about helium-3. So in helium-3, the fermionic atoms form Cooper pairs, but they're in the state S is equal to 1. Okay, so let's have a look then at the possible angular momentum states when you have S is equal to 1. So I can have a state that looks like this, and I'm just going to draw the state in terms of Browse and Ketz like so. So I can have 3 different states. I can have this state, I could have this state. Or I could have this state. In each of these states, if I were to measure the component in the z direction, this would be 1, Sz is equal to 0, and Sz is equal to -1. So these are the eigenstates, and the wave function of the system is some linear combination. So the wave function of the eigenstates. So that's just the spin part of the wave function. But we also have to worry about the orbital parts of the wave function. So in addition to spin states, we need to look at the positional and orbital states. So the overall wave function must be anti-symmetric. Because we're dealing with two fermions that have to be interchanged. And so what that means is, because the spin state is symmetric, that implies that the spatial wave function is anti-symmetric. So what does that actually mean? Well, if it's an anti-symmetric wave function, then the orbital angular momentum cannot be 0. So the first one that you might guess is at the lowest orbital angular momentum state, would be have orbital angular momentum L is equal to 1. So, and I really should say, well, so that's fine. So then what that means is, if I look at the eigenstates, let's just write it down like this. So in other words, if L is equal to 1, then that means that I have the Z component can be 1, 0, or minus 1. So what that means then is that the wave function in the wave function, which will be some psi of r, what are those coefficients? Those coefficients depend on the S state and the L, the angular momentum state. And so how many coefficients are there? So let's work that out. So how many numbers do we need to specify the superfluid state of helium-3? So let's work it out. So the first thing is we need 3 numbers for the spin degrees of freedom. We need 3 numbers for the orbital angular momentum. And then we need 2 numbers for the Bose-Einstein condensate. Why do we need 2 numbers? Well, we need 2 numbers because the Bose-Einstein condensate is condensate of all the atoms in the system condensing into a single quantum state. So all the atoms condense into a single quantum state with a complex wave function. And so because I've got a complex wave function, then what that means is that the number of atoms, the number of degrees of freedom I have is 3 times 3 times 2, which is 18 numbers. So the order parameter for helium-3 is an 18-dimensional object. Which is a lot more than you would have for, say, a regular superconductor. So we describe this using symmetry as follows. Now, don't worry if you don't know any group theory. Okay, we're not going to be using group theory, but I just want to put this out there so you know. So when you hear these terms, you know what they mean. So basically, what you have is you have rotations in spin space rotations in orbital angular momentum, and then you have the gauge symmetry, and I'll say what I mean by that. Gauge symmetry of the wave function. So when you have rotations, they are described by the group SO3, because I've got 3 dimensions of rotations. I've got 3 dimensions in spin space. I've got 3 dimensions in orbital angular momentum space, and because I've got a wave function, the phase of the wave function doesn't matter. Is not observable. I'm going to say but see later. And so that means that if I think of the real parts of the order of the wave function drawn in the Argand diagram, so here is the angle theta, I can't observe the phase, and so that means that I can rotate the wave function in 2 dimensions, in 2 order parameter dimensions. And so this then is the group O2. So we sometimes say that the order parameter is the product of SO3 cross SO3 cross O2, and that is the symmetry group of helium-3 superfluids. So we're not going to, in this course, deal with anything as complicated as this object. There's other symmetry groups that one use to write down the symmetry of the standard model of fundamental interactions and so on and so forth. But once you've got this big symmetry group, it can be broken down into smaller and smaller pieces. And so once one knows the symmetry group, one can use group representation theory and other techniques that are beyond the scope of this course to understand the different phases. So all I want to say, just to conclude, is that this large symmetry group can be broken down into subgroups with lots of interesting experimental consequences. In terms of excitations and topological defects. Okay, so that's where I'm going to finish for today. So next time we're going to start talking more about superfluid helium. So I'm going to stop the recording here, and I'll be happy to stick around and answer any questions.